welcome to UT-ITE series. So today we're very happy to welcome Dr. Mark Fox for our seminar. He's a professor in industrial engineering and computer science, as well as the associate director of the School of Cities here at U of T. We are very happy that Mark was able to book us 1 hour. And so without further ado, please join me to welcome Dr. Fox.
Thank you. I always have trouble giving a talk like this because I don't know whether to talk about the most recent research that my group is working on or talk about a bunch of things. And the reason why that's a bit of a challenge is some of you who have gray hair like me know as the years pile up, you have more and more that you could talk about. And choosing which piece you want to talk about for me, always a challenge. So, rather than just focus on one thing, and as I get older, I actually don't know if I can talk about one thing for an hour straight. I decided to talk about two things with respect to data, with respect to city data, because I was told that this audience would be interested in data as it relates to transportation in cities and stuff like that. So I chose 4 journeys. These journeys are recent journeys. But before I get into them, I decided I might as well give you a little bit of my background, or background for those who don't know me, or for those who think they know me. They may not actually know my background. So I've been around a long time. I've been doing artificial intelligence since 1975. That's my background, computer science, AI, etc. And I started off initially in speech understanding in '75, and I was a member of the team that built the first successful speech understanding system, which was demonstrated in 1976. Back then it didn't fit into your cell phone. It fit on a fairly large computer that computationally and from a memory point of view is insignificant in comparison to what can be packed in our cell phone today. That was a Hearsay 2 system, which was demonstrated in '76. I was responsible for the semantics portion. That is, once words and word phrases were identified, how you string them together to come up with sentences, and determining whether syntactically and semantically those sentences make sense. I also did work in agent-based problem solving, so a long time ago, I started working in the area of coordination theory. Some people way back then within AI thought I was one of the early people in the whole area of coordination, and looked at the application of economic team decision theory, other theories other than the management world that can be applied to design software, and also AI. Also was doing work in simulation and developed agent-based simulation systems back in '80, '81, '82 for primarily applied to manufacturing environments in which we divided every machine became an agent within our simulation. Every work area, cell, etc. became agents to interact with each other. And that was some of the earliest work in the whole area of knowledge-based simulation way back then. Also in parallel, I've been doing work in knowledge representation. So my life in knowledge representation also dates back to about that time, because any type of intelligent system depends upon a rich representation of the knowledge that exists within that domain. And I'll come back to that theme in a little bit. And so developed a variety of knowledge representations and ontologies for manufacturing, engineering, enterprises, and urban ontologies. And in parallel with all that, also worked in the area of constrained directed reasoning, where I did some early work in the whole area of AI-based scheduling as it applies to manufacturing and logistics, etc., engineering design, and urban design. I'm not really going to talk about any of that. And also, I did some work in expert systems. Expert systems are rule-based systems, an AI technology. And surprisingly enough, I designed a steam turbine and generator expert system that diagnoses faults in steam turbines and generators, That was designed in 80-81, went into production use in 85, and much to my amazement, when I checked a couple of years ago, it's in operation around the world still, at over 2,000 turbines and generators that Siemens monitors and diagnoses and repairs. And I had a funny story about that. So when I was looking into whether it still existed and hunted down where it is, it's actually back in the location in Orlando where it was originally delivered, and just that the Orlando location changed hands from Westinghouse to Siemens over the years. And they asked me to come down and visit with them, and I actually met some of the original people who I worked with back then. And what was really scary is the system is by and large the same system with some additions in the area, data analytics, etc. It's a rule-based system which contains over 10,000 rules, etc. for doing diagnosis. And what was scary about it was they brought out the documentation for the system that was written back in 1985, and they asked me to explain to them a paragraph in the document. And I thought that was really strange. Number one, I couldn't even remember writing the document. Number two, I had trouble explaining what I meant in that paragraph. And so it just highlighted, here's a document that's, 25 years old, 30 years old, 35 years old, or whatever. It highlights the issue of interpreting documents that were written hundreds, if not thousands of years ago, what was actually meant by the writers, when I can't figure out exactly what I wrote, just within a relatively short period of time. At the same time, I've always been involved with startups. The surge in interest in AI that exists today is not the first surge. For many of you, this may have been before you were born. So the first wave of AI was in the early 1980s. I co-founded a company called Carnegie Group, which was part of what was called the Gang of Four of AI companies back then. And we created a bunch of products based upon the work that I did here. Simulation craft is knowledge-based simulation. Knowledge craft is knowledge representation language based upon work there. Scheduling work that we did, diagnosis work we did. One of the interesting things about the scheduling work was as it relates to transportation, is we started doing in the company logistics work for the Department of Defense in the United States. And one of the systems we built was logistics systems for moving people, material, petroleum, oil, ammunition, etc. within the in-country area of where the Department of Defense would be deploying their armed forces. And we were doing a demonstration of that system at the annual logistics conference that the Department of Defense would run. And we were demoing it on Iraq. So this was at the time of Desert Shield, which was the precursor to Desert Storm. Desert Shield was when the U.S. was in Saudi Arabia preparing to attack Iraq. Desert Storm is when they actually went into Iraq at that time. We demonstrated a hypothetical scenario of the U.S. forces going around the Iraqis and then in. And as soon as we started demonstrating that, an officer of the Army stood up and said, "Stop, this presentation is now declared, is now classified and only open to people above a certain classification." What we didn't know is that the scenario we were demonstrating was actually the real plan for the United States forces back then. So it's rather funny. Anyway, that system for doing logistics planning in country was then adopted throughout the United States military and taught in military academies and war colleges and stuff like that. We then did the same thing for their medical logistics, their medical airline. I don't know if you're familiar with this, but the DoD runs their own medical airline. So they have a basic problem, which is when people are ill, whether due to battle or just due to the fact that they become ill, they then have to move those people to the appropriate location where they can receive treatment. And so the whole medical logistics system is one of marrying up the individual with the equipment necessary to sustain the person, with the military, medical personnel, doctors, nurses, et cetera, and then and then a plane and getting them going from point A to point B. So we designed and delivered, and they use, probably to this day, the system that we built that was based upon the scheduling work that we did back in the early 1980s. And then more recently, I started Novator Systems, which is an online retail software and services company. Back in 1993, we were probably one of the first in the world to offer online retail software and services. We had a variety of things, such as Virtual Retailer, which was a software package for doing all this. We had a virtual mall operational by 1996 with over 20,000 stores in it. So we were early days for what you now experience online, etc. Anyway, that's sort of my background. Let me skip over. So I've always been interested in how we can get organizations to operate better. I started off within the manufacturing world and applying it there, moved it to the broader sense to engineering and then to organizations in general. And over the last 10 years, I focused my attention more on the urban space problems within cities. Everything that I do has a knowledge representation component to it. What is the nature of the knowledge that exists in that domain that we need to solve problems? How do we represent that knowledge? And then the second part is what's the nature of the reasoning that we want to perform, which constraint-directed reasoning is an example, and I'm not going to get into that side of my life at the moment, or today. So I'm just going to talk about the knowledge representation side. And the problem that I've been concerned with, and others are concerned with respect to the urban environment, is the whole issue of semantic interoperability. And so the question is, what does it mean to be semantically interoperable? It means that we can take data from multiple locations, multiple sources, and we can combine it and then do some type of reasoning and analytics, etc. with that data. Okay? And it seems rather easy. Okay? Why? It's not a problem, one would think, because if you go on the web and you look at all sorts of data mashups, etc., you can see things like this, where we can visualize hotspots of where free Wi-Fi is located, or taxi pickups, or Uber pickups and deliveries, and things of that nature, and you get this wonderful visualization, and everybody's going, ooh, et cetera, et cetera. I'm not a visualization person. I don't get excited about visualization. Because from a research point of view, most of the visualizations I see are quite frankly 30-year-old, 40-year-old technology. Just we have better devices to put it on, so they don't necessarily represent a research problem from my perspective, but that's my view of the world. But from other people's perspective, they really like the visualization. And it's not to say it isn't useful, it's just that from my research view, it's not where I focus my attention. Anyway, so the interesting thing is that in order to do this type of visualization, semantic interoperability is reducible to one single hypothesis. And that single hypothesis is that, let's say we have one data set that generates this data, regardless of what the attributes are. And we have another data set that generates this data, regardless of the attributes are. The hypothesis is that there's a single attribute that is common to both of them. And when we look at those types of visualizations, the type of attribute that we're talking about that's common is geolocation. So you've got longitude, latitude. Okay? So I have a map. That is some type of data. And I have pickups or deliveries, Uber, whatever it is. And that's some type of data. The only data that they share, the only point of intersection, is going to be that geolocation. Okay? And all the other attributes are assumed to be independent of each other, have nothing to do with each other, and therefore, that's our integration of that data. The same holds true if we use the social insurance number. There are a variety of attributes that we can use as a point of intersection between data from many different sources. And we seem to be happy with that, and we take it as a given that we are going to be able to integrate because there is that point of intersection. All the other attributes are independent of each other. Okay? That's a bad idea. Let me give you an example. Now this is 311 data. Okay? Took off the city of Toronto's open data portal. This is an older version of their data because the newer version has less information. But The City of Toronto's 311 data was at that time divided into two parts. You have an ID, creation date, service request name, and then you get more information about that ID. Yeah, so the common piece of information is the ID, and we get further information like the division, the section, and the problem code, which is in addition to what we have over here. This is the New York 311 data. And they have more than this at this time, but let's say they have their ID for this row, they have a creation date, an agency, a complaint type, and a descriptor. Okay. Now, let's say I want to do some type of analysis of the nature of the transportation-related complaints that occur within New York versus Toronto versus Chicago versus Calgary versus whatever. Okay? What I want to do is be able to somehow merge this data or integrate this data or make some assumptions about the equivalency of this data in order to do that. And we do make those assumptions. But let's take a closer look at that. Is service request name the same as complaint type? I mean, that's the obvious inference, right? Is it the same? Well, look at the values. Missing damage signs, street sign, damage. Do they actually mean the same? Let's look at the creation date. 0/1/2010, 4/30/2013. What day is that? Well, we're all relatively intelligent. We know that there aren't 30 months in a year. Therefore, the 30 must be a day. The first number should be the month, and the last is the year because years are 4 digits. So we can, with a high degree of certainty, say this is April 30th, 2013. What's 0/1/2010? Remember something. This is Toronto. That's New York. In New York, if you know anything about the United States, this is sort of a standard for how dates are represented. What's this? I don't have that little piece of information that says either of these numbers is greater than 12. So I can't use that to differentiate whether it's a month or a day. Well, do we have any laws in Canada that say what the standard date is? Date representation is? The answer is no. There's been a private member's bill for some time to try and standardize a date, but I don't know if any of that has been passed yet. But we don't know what that date is. How would we figure out what that date is? Well, we do the obvious thing. We go through the whole data set and we look to see if one of those numbers gets larger than 20, and then we can go back and make the inference that one is a month, one is a day. Missing damage signs, the actual value. This is what's interesting about service request versus complaint type, okay? Is that missing damage signs is that the value here is actually split across two different attributes. So it's not a one-to-one mapping of attributes. I have to have one attribute mapping on two attributes. How do I do that split? And now as I look closer at it, service request name, what does that actually mean? Is it a request for service? This says complaint type. That's a subset of service requests. Okay, so they're complaining about something. Are these really the same thing? I don't think so. So the bottom line is, I've taken some of the simplest types of data that you can possibly imagine that exist between two cities and shown you that there are a number of ambiguities in the interpretation of this data that makes it extremely difficult, if not impossible, to merge it. I can solve the problem of dates. That's not a problem. Okay? But I can't easily solve the problem of how to do the transformation between service request. That's a big problem. Okay? Now, I teach a course. Some of you have taken that course on cities and data analytics. It's part of the city master's program in civil engineering. Okay? And one of the things I tell all the students when they come in, you're going to be spending 80% of your time doing data wrangling, that is trying to get the data to the point that you can actually combine it and do some type of analytics, and you're going to spend 20% of your time doing analytics, okay? I guarantee you at the beginning of the course, they don't believe me. At the end of the course, they absolutely believe me, and I may be too high or too low on the 80% of the time dealing with data manipulation. It's a problem. Okay, so the challenge is semantic interoperability. The problem with semantic interoperability is everybody creates their own data model for their own data sets, have their own assumptions as to what the meaning of the attributes and the values are, and We don't have a clue whether those meanings are equivalent or not. But if we're going to create intelligent systems that are actually going to make reasonable deductions, okay, we have to achieve some level of disambiguity, precision in the representation of data so we know exactly what it means. Now you may say to yourself, well, you know what, we're doing all this neural nets and this data analytics and stuff like that. This appears not to be a problem for neural nets. Well, where are we doing neural nets? We're doing it on images. We're doing it on speech. We're doing it on what type of data? We're doing it from an image point of view on a two-dimensional grid with additional attributes for each cell in the grid. Very simple data. The simplest you can possibly imagine. Okay. Now let's do it for running a city. We don't even know what the attributes are. We don't even know what the classes of information or concepts are, et cetera, that we should be using, let alone be able to build some type of network that can do anything interesting. Anyway, this is an issue. And the source of the problem is this. When people design databases, data models, etc., the meaning of the data is embedded in the code. The only way you can figure out what the data means is by going and looking at the code that creates it, manipulates it, etc. And the whole goal of semantic interoperability is to separate out the semantics from the code itself and associate the semantics directly with the data. So the question is, how do you associate semantics directly with the data? That's where we come to ontologies. That's where we come to where I've spent a portion of my last 40 years or whatever it is in academia. It's not just a reference model. An ontology is a representation of data, of knowledge, that addresses what are the core concepts and properties that span the data, in this case, let's say cities. To what extent can we generalize them and still be useful? Are there a core set of concepts that exist across the city of Toronto? Are there a core set of concepts that exist across cities across Canada? Are there a core set of concepts that exist across cities across the world? If so, what are they? And can I build a neural net that's going to recognize those? The answer is no to the latter. And the answer to the first one is it's difficult. It's a lot of work. And as part of that ontology building, it identifies what the key distinctions are. Okay? I can train a neural net to recognize a chair. I can train a neural net to recognize a stool. Okay? But I can't necessarily have the neural net tell me what's the difference between a stool and a chair. That's still research that's underway in explainability. But the point is, we can say that there is a definition of a chair, and we can say that there's a definition of a stool, and we can use those definitions to identify what the distinctions are between the two, and then to use those to recognize stools and chairs in the world. So the world isn't totally data-driven in our reasoning, where everything just starts with vast amounts of data, and we hope to hell the neural net can be engineered in a way to recognize something. To do reasoning of any type, you need a very rich representation of the world. So if I go back to my cell phone example, in this cell phone, there is a very rich representation of knowledge about the domains that it interacts with. It's not just data analytics. The data analytics, neural nets and other types of technologies will generate what the words are in the sentences. And after it generates it, you have a natural language understanding problem. You have a problem of connecting what the natural language understanding generates to a model of the world that exists in here. And a model of the world that exists in here is a model of you, your activities, other resources, apps that are inside of this, etc., which you know nothing about being there, but that ontology is in there also. So the question then is if I'm going to create precise representations, we have to be able to represent the key distinctions so that our reasoning systems can actually do interesting reasoning about the world. Now, let me make that a bit clearer. I gave the stool versus a chair. It turns out the stool is really a subclass of a chair. Because if you think about it functionally, all a chair is something you can sit on. And then there are variations on that theme in terms of how structurally they exist. But let me just see where I am with this. Well, let me give you another example of precision in representation. Anybody here originally from a warm climate? Okay. What's the average temperature where you were born?
Around 28.
28. Okay, 28 degrees. I spend a lot of time in Singapore. It's 33 degrees. It's humid every day. Day in, day out. Because of winter. If you ask the question, what is your conceptualization? What is your definition or description of snow? When you were growing up, what was your conceptualization of snow?
It's something cold.
There, exactly. And why is her conceptualization of snow something cold? Because from a day-to-day perspective, that's all she needed to have in terms of a representation of snow. Okay? Now, imagine you're a ski instructor in Banff. Okay? What's your conceptualization of snow going to be? It's going to be a lot more detailed. Why? Because where you're going to ski, what type of skis, what they still put wax on skis. Anybody ski? I don't know. Back when I skied, we still put wax on skis. Just okay. A lot of what I would do on that particular day was based upon my more detailed notion of whether I have powder snow or popcorn snow or ice or slush or whatever it was, etc., to allow me to determine what are the best tools for achieving what I want to achieve. And this is true of life. The precision of the knowledge that you need to bring to bear is dependent upon the type of reasoning you have to perform. Weak representations, that is, representations that don't contain a lot of properties and detail, are appropriate when the nature of the inferences or reasoning you need to perform are relatively weak. Okay? So, if it's snowing outside in Singapore, all I need to know is stay inside. Okay? Whereas if it's snowing outside in Banff, there's a lot more interesting things I want to do. So, when we... Okay. So when we talk about ontologies, we really talk about three different levels of an ontology. The lowest level is what we refer to as a knowledge graph. It is basically the equivalent of a network representation, or what most people would see sort of in a database. It identifies the classes and properties, maybe has taxonomic information. The next level is what we refer to as the definitions. And the definitions tell us what the meaning is of those classes and those properties. So we have a language, usually a logical language, that we can use to define the meaning of our terms in our representation. And then the third level is what we refer to as microtheory. It's a set of axioms or rules that allow us to perform certain types of deductions. Beyond that is supported in the definition of constraint. So if we look at 3.1.1, you start off, you create a taxonomy. In this case, here's the, we go back to the types of service requests that exist within 3.1.1 in Toronto. We have reports, requests, complaints, compliments, and within reports we have abandoning, forbidding, noise, odor, or request for action, request for information, complaints, etc. Step 2 is filling in the data properties, basic things like that are numbers and strings, and then you have your object properties, which are relationships between one concept and another within the system. So we can see that a 3.1.1 type has a subject, has an action, etc. We're not really at the ontology level because we've yet to define anything. This is all the building blocks. The next level is when you get into the definition of concepts, okay? And we use the language of logic. There's multiple languages that are available. The one we use is description logic because it's well supported on the World Wide Web, the Semantic Web. And they define what properties are necessary for an instance to be a member of the concept and what properties are sufficient for an instance to be a member of the concept. What does that mean? Well, you have to understand it in contrast to a database. If I have a database and I have a data model, everybody here is taking a database course or at least used a database and by association has learned what a data model is. So what's a data model? In a relational database, you have something called a relation. Let's say we give it a name, and that name is service request. And then that relation will have a set of attributes. And one of them may be called the ward, the status, open time, close time. And that's your relation. If you're lucky, there's type information that tells you that this is a string or that this is an integer or real. It may say that this is a link, an ID that links to another relation, to an ID in another relation. But there's no information there that tells you which of these properties are actually necessary or sufficient for being a member of a service request. Okay? So I could create a relation called chair, and I could put back, number of legs, things like that, attributes like that. There's nothing in the data model that tells me which of those attributes are necessary or sufficient for being a chair. Because I could also have manufacturer, manufacturing date, composition, material. Which of those are necessary to the definition of what a chair is? The answer is there's a whole bunch of stuff that's unnecessary, and there's a bunch of stuff that is absolutely necessary. But being necessary does not mean being sufficient, okay? What does that mean? If I say that you are a Canadian, it is necessary if you are a Canadian citizen for you to either be born in Canada or to receive citizenship. Okay? It's necessary. But is that sufficient? Not necessarily is it sufficient. So you could come to me and you could say, here's my friend Fred. He's a Canadian citizen, okay? And I say, oh, Fred, where were you born? Okay, born in Geneva. Oh, okay. When did you receive citizenship? Well, I don't have a document. Doesn't satisfy the necessity clause. So, by that alone, not a citizen. Okay? But let's say Fred comes in and says, I was born in Toronto. It's a necessary requirement to either be born in Canada or go through the citizenship process. But just because they're born in Toronto doesn't mean they're a citizen, right? Because they could just move to another country that doesn't have dual citizenship. As a part of getting citizenship in the other country, they have to give up their citizenship in Canada, and this person may have given up their citizenship in Canada. So it's a necessary requirement, but it's not sufficient for determining citizenship. That's a distinction between necessary and sufficient. I can tell you whether you could be a citizen, but I can't absolutely say you are a citizen. That's necessary. And by necessary, I can also tell you whether you probably aren't, because you don't satisfy the necessary conditions. So the definitions here allow us, oh boy, I haven't even gotten out of ontology and I'm 42. Okay, this is going to have to speed up. Okay, that's enough on that. Why would we define concepts? The whole point is we want to achieve semantic interoperability. Greater precision in definition of classes, concepts, reduces ambiguity, interpretation, enhances integration of data. Validity analysis, we can use these definitions to determine if the model is valid. What do I mean by valid? I may have a definition of a truck, and I may have a definition of a car, and I may think my definitions are good enough to distinguish between the two, but in fact they aren't. We can automatically determine whether they are the same things, different things, or they're defined in ways that are invalid, just by using logic. I can do consistency analysis, determine whether anything that I said is a truck is actually a truck, so is Fred's truck actually a truck? I can use a definition to determine whether that's the case or not. And I can do automated classification. This is actually very interesting, because as the volume of information continues to come in, at very high speeds, large volumes, how are you going to classify everything that comes in? I get sensor data. I group the sensor data. What does that sensor data represent necessarily? I can use my definitions to say, that's a truck. Okay. I'm going to skip over some of the So, I'm going to go through 4 journeys. I'm going to have to do 4 at a 4-minute pace. Do we have time beyond 1 o'clock, or is it?
Would be better to finish a bit before 1.
Finish before 1, sure. Okay. Let's see. I'll go through the first 2, because the first 2, well, I'll go through the first 2. The first journey here is one I started about 10 years ago, 9 years ago, 8 years ago. 8 years ago, 7 years. 7 years, okay. And the problem was that the problem that I was introduced to by Patricia McCarty of the Global Cities Institute here was that cities around the world use some way of measuring their performance. And they're often referred to as indicators. And the World Bank and the province of Ontario asked Patricia and her group, can they go and determine what indicators are being used by cities and whether they're consistently applied. So they went and talked to, I don't know, was it 9, 10 cities in North and South America, and created a catalog of all the indicators that they were using, and they found out that there were 1,100 indicators that were being used across the 9 cities. Now, anybody want to guess what percentage of those indicators were equivalent to each other or comparable? Any guesses? You can give me a percentage, okay? Just give me a percentage.
50.
50%, thank you very much.
10.
We got 50% there. Anybody want to give me another?
10.
10, okay, so now we're bounded. Okay, we'll say between 10 and 50. So 10% gives us 110, and 50% gives us 550. Okay, great. 2. Okay, so whenever you read about smart city awards given to Toronto, Columbia, wherever, Bogota, wherever, it's all based on bullshit. Okay? Because the data that they're using, the indicators that they're using are not really comparable. Well, sorry, I don't even want to say the data isn't comparable. I mean, that's absolutely the case, the data isn't comparable. But on top of that, the indicators that they're using are not necessarily defined the same way, and hence not comparable. So it's sad. And you would think that in the world of finance, where there are well-known theories and concepts, etc., that have been standardized on a worldwide basis, that it would be better in that area. Well, if you talk to Enid Slack, who's head of the Institute for Finance and Municipal Finance and Governance, she'll tell you the same thing exists within the finance world. It's no different, even though they appear to have a much better terminology with unambiguous interpretation. Okay, so as a result of that, Patricia and her team led the effort over at ISO, the International Standards Organization, to create 37120, which is a set of 100 indicators spread across the themes that we see here, to create a standard that cities would use. And as a result of that, cities like Toronto, etc., have adopted this standard and are publishing what their indicators are according to the ISO standard. And let me give you an example. One of them is primary education student-teacher ratio. The number for Toronto is 14.6, which is a combination of both the Toronto District School Board and the Toronto Catholic District School Board. Okay? And we know what the numerator and denominator is. Okay, how many students, how many teachers are across all that to get that number? 14.6. We got a problem. This isn't displaying properly. I don't know what happens when we go from one machine to another. Toronto is 14.6. Okay, and I was doing work with a group in Melbourne, and they said that their number for the ISO standard is 24.1. And the question is, why are they different? Whoops. Don't want to show that yet. Why are they different? Okay, now, you have to understand, I was on a conference call with the people in Melbourne, and the research associate was accusing me of lying, that the number that Toronto has is incorrect and I'm lying. I had nothing to do with this. I'm just reading a number out of the document that the City of Toronto provides. Okay, but they were personally incensed at the fact that Melbourne was almost twice as bad as Toronto. Okay, and so what it really means is, what do these numbers mean? Well, it's really just a beauty contest. Okay, and that's all you can really say. And beauty is in the eye of the beholder, and there's not much you can say about it because all we got are those two numbers. And if you really want to understand why are we 14.6 and why is Melbourne 24.1, you need to start looking at the data that underlies it. So now we're back to data. Okay? And so what was the data used to derive this? What was the data used to derive that? Well, to answer that, we first have to understand what data needs to be used to derive it. And if you go and you look at the definition of primary student-teacher ratio, they talk about not including private educational facilities, not including administrative staff, not including kindergarten or preschool, and it goes on and on and on, the things you don't include, in addition to things you do include. And so I guarantee you, if you go and you look at the underlying data, that you'll probably find things that are not supposed to be included that are included in the analyses that are performed. So we did that. We went out onto the web and went to the open data portals of Toronto and to get all the education information. It turns out to get education information, you have to go to district school boards because school boards are run by the province, not the city. But we'll leave that as it is. We went to Melbourne to get all their open data as it relates to the derivation of all this education data. And what did we find? Anybody want to guess? Nothing. There's nothing there. Okay. We live in a world of open data. Okay. That's bullshit. There's a little bit of open data. There's not much open data that is truly relevant to what you want to do. And as all of you know, because you're into transportation, to get the data you really want, you got to start talking to people. And you got to pry it out of their hands. I can tell you a story about trying to get homeless data in the city of Toronto. Now that's fun. Okay, so we have this project called the Polynosis Project. It has a set of goals. Number one, we try and inform cities as to what they need to publish on their open data portals, because we're not publishing a whole lot of anything. Two, we want to tell them how to publish it in terms of what the format is, what the vocabulary is, what the ontology is. So our goal is to provide standards for publishing that data. And third, we want to support automated analysis, because the whole notion that if you publish it, it's Field of Dreams. You ever see the movie Kevin Costner? Field of Dreams? He builds a baseball field in his cornfield. Everybody thinks he's nuts, but he hears this voice in his head says, if you build it, they will come. Anyway, if you haven't seen it, it's a great movie. It's a tearjerker type movie. But anyway, the thought of open data is that we can make it available. Citizens, unlike yourselves, because you're actually equipped to do data analysis, but the vast majority of people out there are not equipped to do data analysis, that citizens will go and do the analysis. Well, that's bullshit too. And so our goal here is to provide tools to automate the analysis of city performance, perform longitude and transversal analysis, determine root cause differences. So I'm going to skip end. What we want to do is to build this intelligent agent so that it's indicator independent, that it doesn't know anything about indicators, and that it's city independent, it doesn't know anything about the cities. And so that results in a system, that results in a system that has to take as input the definitions of the indicators, knowledge about certain themes of knowledge, like what is a student, what is a teacher, what is a classroom, if we're talking about education indicators. Specific knowledge about a city, like secondary school in Quebec, what does it go up to? Grade 11. Secondary in Toronto goes up to grade 12. What's a private school in Toronto? School not supported by the government, right? You have to pay tuition to use it. What's a public school in the UK? It's a school not supported by the government. You have to pay tuition in order to go to it. So even the interpretation of what's private versus public changes if you just use the data directly. Anyway, and you have to get the actual indicator data. And you need an ontology to represent all that so that we have commonality, precision in the representation and its interpretation, input that into our engine, and then we can begin to do analysis of any city for any indicators using whatever data that they provide. And so I'm not going to go through the representations, I don't have time, but there are ontologies, there are a large number of ontologies that have been created, starting from the most foundational of time, provenance, place names, activity, state, resources, and then going into health, transportation, shelter, et cetera, et cetera. We even have built an analysis system that can actually compare the same city over time to see what the source is of change based upon the indicator data, and also what the comparison between cities. And what's really interesting about that is, if you think about that data I pointed to from the city before, it gave us the numerator and the denominator, right? It told us how many students, how many teachers. Now, if I told you the indicator went up over time, our student-teacher ratio went up, or let's say it went down, and I gave you the numerator and the denominator, does that tell you anything? It doesn't tell me anything. It just tells me either the number of students increased or the number of teachers increased, or the other way. I mean, it's 3 times 3. Increase, decrease, stay the same, increase, so. We have 9 alternatives. Let's look at the city and why something would increase or decrease between 1990 and 2010. Well, if we know the number of students and teachers, it doesn't really tell us anything, but if we know how to define what a student is, think about this. What might have been the difference between 1990 and 2010? The definition of student may change. If we go and integrate special needs students into our general population, that then results in a lower student-teacher ratio because special needs students have more teacher support. And all that gets integrated back in, it reduces our student-teacher ratio, and it's because we changed the definition of the student. Another source of why change may occur is what happened between 1990 and 2010. We had amalgamation, 1999, something like that? We amalgamated in the surrounding cities, and they had different student-teacher populations, student-teacher ratios, and that results in a change in what's going on. So in order to understand and figure out what the cause of change is, in this case we have to understand what the definition of the student is. In this case we have to understand what the definition of city is. It's not just numbers. Okay, and this work is now being standardized as ISO 21972, which is the next to last stage of being accepted as a standard. Let me talk about transportation planning. And I've got to be very careful here because you're all transportation people and Eric is sitting there. So now I was going to say I feel nervous, but quite frankly I don't. We're too old to be nervous about that. What's the challenge when it comes to semantic interoperability? So we have this project, it's a tripartite project between Hong Kong, Toronto, and Utrecht. Okay, and we want to share data. We have the same problem. Share data between the different locations, we have to adopt a common representation. To adopt a common representation, we have to choose one, and what you discover is there is nothing available, and so that results in the need for some type of ontology. But it's not limited to sharing data between cities. It's also something that occurs within a project itself. So this is the old diagram. I don't even know if there's a new diagram, but it's a diagram of the iCity project, which Eric is the head of. And it is integrating a whole bunch of other projects, complete streets, parking management, transit management, etc. And there's all sorts of other stuff, and it encompasses a number of faculty members that are within civil engineering and outside. And we have a problem in that we have to achieve intra-project interoperability. How do we take data from complete streets and parking management, transit management, if they're done by different faculty, done by different students who've created their own data models, gotten their own data, etc. How do we then combine all that? And the answer is, well, we've got to create a project to create an ontology to achieve interoperability, and that's what we do. And so we have I forgot to mention that Megan Katsumi is the lead on this, so I want to acknowledge everything that she's been doing. And we've developed ontologies for representing location, time, monetary value, change activity, person, organization, household, buildings, vehicle, travel numbers, transit, transportation network, parking, etc., that can be used as a basis for communicating information from one application to another, for building other applications on top of that. We have, as I said, developed the ontologies where we just not only say there's a transit vehicle, but we then define what a transit vehicle is using description logic so that we have a more precise representation of the concept of a transit vehicle, of a household vehicle, etc., so that we can then use it for classification, identification, and just being able to more precisely say, if I'm getting data from Hong Kong, they need to be able to translate what they have into the standard so that we precisely understand what they're representing. I'm going to skip over that. I'm going to skip over that. I wanted to get to this. And this is a visualization, which you haven't seen yet, Eric. And what this is using a tool called LD Reactor. And what it does is it allows you to create reports, if you will, of data that's represented using ontologies. Okay? And so if you translate your transportation data into this ontology, then you can go in and start using this to display the data in many different ways. And this allows us, in this case, we selected activity at destination. What are the activities at the destination? Is it home-based activities, work-based activities, et cetera, et cetera. Lots of others doesn't appear here. It allows us to identify from a mapping point of view what are the zones where things start, et cetera. It now gives us a single tool so that if all the different projects map into our ontology, we can provide a single mechanism, a tool by which we can start investigating the data, pulling more information out of it, et cetera, et cetera. So the least result of adopting an ontology means that other tools now become available to you to be able to either visualize, analyze, report, things of that nature. So we have that there. And I better stop now. Let me go to the end. Most of the stuff I was going to talk about is in the social services area. So, in conclusion, everybody uses the word data. It's not just data. To me, data is a pejorative word, okay, because it does not recognize the complexity, the depth and breadth that exists there, that you have to ferret out and figure out whether it's relevant. And then you've got to begin to formalize it so that we have precise definitions. The bottom line is our ability to reason about a problem and find solution is limited by the richness of the underlying representations. The more incomplete a representation is, the more limited the reasoning is going to be. We just know that. In AI, we've known that for 40 years. And all of knowledge representation ontologies is built upon that understanding. And so, why am I here in front of transportation people? Because we've been working on that as part of the ICT project, and as part of other projects. We've been developing those ontologies, which hopefully will become a standard. And in fact, we have now proposed to ISO a new standard for transportation planning ontologies that has been approved at the Canadian level, has been approved at the ISO level, and we will begin working on that. There's going to be 4 parts to it, but I won't go into detail. I guess I'll end there. So hopefully you'll come away with some understanding of why Mark Fox spends time on ontologies, and what they are and what value they have. And I'm happy to talk to you at any other time. Thank you.
We have time for a couple of questions, and then I'm sure you can ask more questions.
Sure. Any questions? Yes.
You started by giving an example when you're trying to merge 2 data sources based just on geolocation. What do you think are some most common specific to geolocation joining semantic interoperability issues?
Sorry, I didn't
So
get...
what are the common issues?
What are the common issues?
Interoperability if you are talking about geodata when you are merging geosources.
Well, I mean, the interesting thing about geosources is that there have been standards group working on creating standards for representing geodata for a long time. And if there's anybody in the world that's a lot further along in these standards, it's them. I can't say what the problems are for just geolocation, because geolocation is as simple as a longitude, latitude. It is as more interesting in terms of administrative areas. It is more interesting when we get to maps and the representation of physical transportation paths versus logical transportation paths. So it depends how far up the conceptualization you want to get into in what could be referred to as geolocation. Okay. So the launch that's dealt with. There are standards for dealing with that. Administrative areas, there's a variety of organizations over decades that have dealt with that. Maps are becoming more standardized. Any other questions? Going once. Going twice. Yes.
I thought you made a really good point about some of the data visualizations being a little, we'll say, overrated. Are there any techniques that you find particularly interesting that are more modern?
Oh, gee. Because I'm not interested and I don't focus on it, I can just tell you an old story. Back in 1981, I started a project which we called Autograph. And the goal of Autograph was to automate the generation of graphics from data. That's 1981. And so we had a variety of visualization techniques, and based upon the underlying semantics of the data, we would then combine those visualization techniques to generate more interesting visualizations. That's when I finished looking at visualizations, which is really back in the 1980s. And people in my group, in my project, then went off and started companies which were bought by other companies, et cetera, that productized all that stuff. I have to be careful. I say things that come back on me now and then. So as an example, I don't know. I really don't know of any good visualizations. What do you get in a simulation? How do you visualize simulations? I mean, I was on a review committee for somebody who visualized the supply chain, okay? And what they showed was trucks moving, little icons of trucks moving, okay? It was fun to see if you're a high-level funder who knows nothing about the technology and you get off by pretty pictures, but it didn't say anything to me, and I quite frankly told them that to their face. I didn't get invited back to the next review. So I actually don't run into visualizations that I look at and say, this is truly meaningful. And the reason why is data is so complex. It's again this data. Visualize the data. we trivialize the notion of data to the point that we actually think we can do things with it. And visualization is one of them. It is so difficult to visualize anything beyond, let's say, 2 dimensions. Go to the city of Toronto has, I forget, I don't know if it's called Healthy Cities or whatever. They have a visualization, okay, of cities. So you can see the different neighborhoods. They break it down into whatever the number of neighborhoods are. And they can then overlay colors of different density based upon, so you could have you could show population in terms of different ages. You can show income, you can show et cetera, et cetera. Once you overlay more than 2 variables, the visualization is uninterpretable. Okay? So I haven't seen anything that really excites me. And there may be lots of stuff out there, and people will come to me afterwards and say, let me show you my visualization. I'll get really off on that one. But I really don't run into it that. I sort of fall asleep during the midst of it. The only good visualizations I've ever run into is when people are doing computer-generated animation, fun stuff. It has nothing to do with data visualization, just fun computer graphic animations. So I haven't seen anything that excites me yet. And quite frankly, I've looked at, and I won't name them, different groups who do visualization and try and do visualization of the urban environment, and I have not been excited yet by what I've seen. So, sad to say. I can't give you an answer as to what it is. Okay?
All right, I think we'll stop here, but if you have more questions,
Great. Thank you very much. Thank you.